Hey, welcome to another pre-recorded lecture. And yeah, I'm gonna try to explain the remaining piece about generated functions, which is gonna be the compositional formula. And then I'm just gonna slightly compare it to compare exponential to ordinary generated functions to see what the main difference is between the two. So let me remind you what we did last time. Yeah, that's last time I was doing the exponential formula. For that, I need the notation pi of bracket n is the set of set partitions of bracket n, and the cardinality is given by the Bell numbers for which we computed the generated function last time. And then there was the exponential formula, which tells you that if you have a sequence, if f of n is a sequence with f of 0 equal to 0, and then you can define another sequence h of n given by h of 0 is 1 and h of n is the sum over all set partitions of bracket n into arbitrary number of non-empty blocks, f of the size of S1 times f of the size of S2, etc., f of the size of Sk. So this is for n greater or equal to 1. Then the exponential generated functions satisfy this rule where you just take the EGF of h is given as the exponential of the exponential generated function of f of n. Yeah. So today I'm going to discuss a generalization of this, where instead of the exponential, you just have some other function g. And well, so that's called the compositional formula. Compositional formula. So again, yeah, I can even just copy. The statement of the exponential formula and then modify it in a certain way. First of all, the name is different. Okay, so the setup is the same. You start with a sequence f of n, f of 0 is 0, but you also want to, okay, let me move this a little bit. I'm also going to have another sequence. Let g of n be another sequence satisfying g of 0 equal to 1. Okay, so I have two sequences. One is, and they have different initial conditions, different constant terms, or whatever. Then if you define h of n by the same stuff, h of 0 is 1, except that here in this formula I multiply the result by g of k. Oops, yeah. So in other words, right, k, as you remember, k is not fixed. K varies, as depends on your chosen set partition. And so what this means is that you apply, so you split your bracket n into some non-empty blocks. Then you count the number of ways to perform the f task on each block, and then you also count the number of ways to perform the g task on the set of blocks. Right. So the blocks are like your connected components, and then so you choose f on each connected component, and then you choose g on the set of components. So maybe you want to order the components or choose a subset or color them in some way. So that's this way each set partition now has a weight, which only depends on the number of blocks. Yeah, and then then the claim is that instead of the exponential function here, I'm going to put g of f of x. So that's the statement of the compositional formula. And let me remark. Yeah, and even, okay, here is the proof. Proof is the same as the proof of the exponential formula. Which is to say that, okay, for the exponential formula, what we did was we fixed k. So we fixed the number of, yeah, maybe I should write down a little detail. So for if you fix k, then for the case of the exponential formula, the generating function was given by f of x to the k over k factorial. But now, because we multiply, so g of k is going to be constant. It's not going to depend. It depends only on the number of blocks. So it's going to be multiplied by g of k this time. And then you just sum over all k, and then you get, just by definition, g of f of x. Right? It's just by definition the sum of all these things where k runs from 0 to infinity. This is equal to h of x. Yeah. So yeah, the proof is very much the same, but this is more general, and because this is more general. So remark is that you get the exponential formula, get the exponential formula for, so g of x have to be equal to the exponential of x, which means that a little g of n has to be equal to just 1 for n, for all integers n, right? Because remember, all these are exponential generating functions. So, and that makes sense, right? So for the exponential formula, we didn't have any term here. That corresponds to g of k being equal to 1. Yeah. And now I want to compare the result. I want to kind of, last lecture I ended up with a nice result for n factorial. Right, let me remind you what we did in the last lecture. It was that I was trying to count the number of ways to split n people into non-empty groups. Have each group sit around circular table. So the number of such ways was given by, surprisingly, n factorial, using the exponential formula for the generating function. And yeah, I even gave an example. So there was like 2 arrangements where all people sit at the same desk. There is also 1, 2, 3, 1, 3, 2, and also 1, 1 and 2, 3, and there was also the singletons. So that the answer is 6, which is 3 factorial. So today I want to crank it up a notch. I want to, so for each circular table, I want to sit around the circular table and right, so each group sits around its own circular table, and to continue the wedding analogy, I want to choose, I want to color each table in one of two colors, which, yeah, I'm going to use the wine analogy. It's a good analogy. So sit around a circular table and choose to serve a red or white wine at each table. So let me denote this new number by h of n now. H of n is you split people into groups, sit each group around a circular table, and then you also choose one of the two options for each table. So the more tables you have, the more the weight is going to be. So let me try to count. Let me try to count the new number. By the way, feel free to pause the video and try to guess the formula based on what you know about generating functions, or maybe you can find a bijection, but this also turns out to be a nice number, which let me try to compute it for this example here. So on the left I have only one table. So one table, there's going to be just two options for each of these tables. So this gets multiplied by two options, right? Now here I have two tables. So I have 4 options for the wine in each of the two tables. And finally here I have 3 tables, so I have 8 options. Now 2 plus 2 plus 4 plus 4 plus 4 plus 8 is 24, which is, so the new h of 3 is 24, which is quite suggestive. So okay, how do we compute the general formula for the h's? Well, we have to use the compositional formula. So, and that's going to be very similar to the previous lecture. So here's what I'm going to do. I'm going to, as in the previous lecture, I'm going to consider f to be the number of circular arrangements. F of n, which is 0 if n is 0, and n minus 1 factorial if n is greater than or equal to 1. That's the number of permutations modulo cyclic shift. Okay, but now I also have the function g. Right? I also have each set partition is weighted by, in this case, 2 to the number of tables, 2 to the number of blocks. So g of n is equal to just 2 to the n. So now I can compute the exponential generating functions. And for the f of n, I computed it last time, right? It was f of x, it was a negative natural logarithm of 1 minus x. For g of x, well, this is very easy, right? It's the sum 2 to the n, x to the n over n factorial. So it's the exponential of 2x. I think. Yeah, okay. So, okay, and now I can just literally apply the compositional formula. So I get is h of x is given by the exponential of, so I need to take the composition of g of f of x. So exponential of twice, well, negative 2 times the logarithm of 1 minus x. So it's 1 over 1 minus x squared, right? So I need to extract the coefficients of x to the n over n factorial. So okay, now as mentioned in the previous lecture, I can view this as the derivative. And this is the derivative of what? It's just 1 over 1 minus x prime, right? So okay, I know how to take derivatives in the land of formal power series. So I 1 over 1 minus x is just the sum of x to the n. I take the derivative, so I get n times x to the n minus 1, I think, or maybe wait, should I, when n is equal to 0, this is okay. Yeah, I can write n plus 1. I'm gonna shift the index in a little bit. Right, so I'm going to take the derivative of x to the n plus 1 here, and I get n plus 1 times x to the n, and now n runs from 0 to infinity. So, okay, but still I have to take the coefficient of n of x to the n over n factorial. So it's x to the n over n factorial multiplied by n plus 1 factorial. So the answer is the new h of n is n plus 1 factorial. And again, as usual, the challenge question is to find a bijective proof. So the plan was that maybe originally it's easier to do bijections, but after a while it's yeah, it should, for this problem it should be very hard to find a bijective proof to demonstrate to you the power of generating functions. But that is to say, sometimes bijections work better. So you have to, the trick is, like in lectures, I usually just give you a formula and then give you an example. But in practice, you're going to have a problem, and then maybe you need to apply several different formulas, or the first trick is to choose which formula to apply, and whether to apply a bijection or maybe to combine a bijection with some. Anyways, I have given you lots of tools, and maybe what I'm doing looks easy, but once you see the problem, it's gonna look tricky. Yeah. So that's the compositional formula, and that's basically that's all I wanted to say about generating functions. One last thing I want to say is that I want to compare the exponential to the ordinary generated functions. So exponential versus the ordinary generating functions. Because, so I didn't even give you the formulas, but there are the analogs of some of the formulas we studied, not only for exponentials, but also for ordinary generating functions. So let me try to highlight the main difference. Let's say, in all I'm going to say, there is going to be, you have two sequences, f of n and g of n. And I'm going to try to explain the combinatorial interpretation. So I'm going to think of f of n as the number of ways to carry out some task on the set bracket n, and let g of n be the number of ways to carry out some other task. Some other task on bracket n. Yeah, so what I'm going to do now is to compare the product formulas, the compositional formula, and the exponential formula for each of these, for each of these two kinds of generating functions. So, and the main idea is going to be that so let me write it down, even though it may not make sense right now. Main idea is that the exponential generating functions correspond to labeled elements. Well, I think I called them distinguishable. Okay. So when you take the exponential generating functions, that means that the elements of let me say this more carefully. So when defining h of n from f of n and g of n, if you deal with the exponential generating functions, that means that the elements of n are distinguishable, and ordinary generating function means that the elements of bracket n are indistinguishable. Or in other words, for the exponential generating function, h of n is defined by choosing subsets of bracket n, which could be empty or not, well, could be non-empty or whatever, unordered or ordered, but they have to be. It matters which subsets you choose. But for the ordinary generating function, h of n is going to be defined by choosing intervals of bracket n, yeah. Which so in other words, the idea I have in mind is that if you represent bracket n by some collection of balls, right? 1, 2. If the balls are distinguishable, then when you choose a subset, maybe 1, 2, and 5, and 8, it matters which balls you choose, right? So balls are distinguishable, then you choose a subset of balls for h. Now, if the balls are indistinguishable, then when you choose, it doesn't matter which subset you choose. All that matters is how many balls you choose. So here I chose 4 balls. I may as well have chosen the first 4 balls. So that's you choose an interval. An interval, it doesn't matter which one, only matters how many you choose. And here you choose a subset. Anyway, it's going to be clear from the statements what I mean, but so far it may not be clear. So yeah, let me give you, for each fact I gave you about the exponential generating functions, let me give you the analogous fact for the ordinary generating function. So the first one was the product formula. which for the exponential, yeah, maybe should I even try? Okay, for the exponential generating function, the product formula looked as follows. If you multiply h of x is equal to f of x times g of x for the exponential generating functions, then the coefficients were going to be given by there is an n choose I times f of I times g of n minus I. Okay, and for the ordinary, let me try ordinary generating function, if you have h of x equal to f of x times g of x, then the product formula was that h of n is the sum f of n times g of n without the extra n choose I here. So, and the combinatorial interpretation was that the h of n is the number of ways to choose a subset, S of bracket n, and then carry out first task on S, and then carry out the second task on the complement of S. And similarly, so what I'm gonna in this case, so to get this, in this case you would get the formula for the exponential generating functions. Now let me try to write down the analogous interpretation which kind of applies to the ordinary generating functions. So here it's going to be the number of ways to choose not a subset but an interval. Choose not a subset but an interval which is, so you just your interval is going to look like this. It's going to be just the first several elements, 1 all the way up to I, subset bracket n. Could be empty, right? Because I goes from 0 to n. Could be empty, could be the whole thing. And then you carry out the first task on this interval, 1 all the way up to I, and then carry out the second task on the remaining interval, I plus 1, I plus 2, all the way up to n. So you see what I'm doing here. I'm just replacing subsets with interval, and I get formulas for ordinary generating functions. Okay, now that's the product formula, and now I'm going to also explain the compositional and the, well, yeah, in the class we first did exponential, then compositional, but it's going to be easier for me to start with the compositional formula. So yeah, let me try to draw the pencil line here. It's much better. Okay, so what was the compositional formula for the exponential generated functions? Well, okay, so here on the left I'm going to have the exponential generated function. So, okay, and the compositional formula was going to be h of x was going to be equal to g of f of x. In this case, h of n was the number of ways to partition to choose a set partition bracket n into non-empty blocks, where the order of the blocks doesn't matter, and then you carry out first task on each block, and then carry out the second task on so the first task is the f. This is the one counted by f of n. The second one is counted by g of n. F of n. Second one is g of n. Second task on the set of blocks. So that's the setup of the compositional formula for the exponential generated functions. Now I'm gonna try to do the same on the right-hand side. So here I'm gonna have ordinary. First of all, let me try to erase the red stuff. Okay, ordinary generated functions. When is the compositional formula true for ordinary generated functions? You have two sequences and you want to define a new one, so you want to give like a combinatorial interpretation of the composition of ordinary generated functions. So it's going to be the number of ways to again, what I'm going to do is I'm going to replace the word blocks with so you want to partition in the set bracket n into a number of non-empty intervals. Carry out the first task on each interval, carry out the second task on the set of intervals. And that's it. So here, what do I mean by partition of bracket n into non-empty intervals? Means you take bracket n and then you just split it into into chunks of consecutive. So it's like 1, 2, all the way up to I1, union I1 plus 1, all the way up to I1 plus I2, and etc. Union, etc. Blah, 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 comma, n. So the point is that you partition your numbers into consecutive intervals. And each has to be non-empty for the compositional formula to work. Yeah, and finally, all I have to do is say what happens with the exponential formula. So, and the exponential formula is going to, here I have a problem with the terminology because the exponential is already, the term exponential is overused. So let me try exponential. I'm going to put it in quotes because, I mean, it is the exponential formula, but here all you have to do is just, what I mean by that is the specialization where I'm going to assume that g of n is equal to 1 for all n. Because that's the specialization that we got on the left. So on the left, instead of g of f of x, you're going to have this equal to the exponential of f of x. And h of n is the number of ways to partition bracket n into non-empty blocks, carry out the f of n task on each block, and that's it. So I'm just going to erase. And that's it. But on the right hand side, it's going to be different, right? So let me try to let me fill this out later. But what I want to say first is that let me do it this way. So I'm gonna move all this stuff down. So if you have an ordinary generating function of g of n, right, that's g of x is equal to the sum n greater or equal to 0, g of n x to the n. And because I'm assuming that g of n is equal to 1, instead of getting the exponential like on the left, I'm going to get just 1 over 1 minus x. And in particular, if I now apply the compositional formula, what I'm going to get is 1 over 1 minus f of x. So an h of n is going to be the number of ways to partition bracket n into non-empty intervals, carry out the first task on each interval, and then that's it. So here the formulas actually look different. The proofs are all the same, and that's it. Yeah. So, right, if you take 1 over 1 minus f of x and you apply the definition of composition of functions, this is going to be the sum of f of x to the n, just the sum of f of x to the n. And each individual term is going to be, well, maybe I should use f of x to the k, and the sum of k greater or equal to 0. So each individual term is responsible for, by the product formula, for each individual term corresponds to the case where you have k intervals. So you fix the number of intervals, and then you get f of x to the k. That's the ordinary generated function. Because the intervals are going to be ordered, you don't have to divide by k factorial. Yeah. So that's the sort of the proof sketch of this result. But in general, it's a special case of the compositional formula, which also they all have the same proof. So during the previous lectures, I only tried to discuss the exponential side, not to get you confused. But now I think if you just put them all side by side, you see that the difference is always just you replace sets or blocks by intervals. And that's it. So yeah, that's all I wanted to say about generating functions. And when we come on Wednesday, I'm gonna explain some applications, how to count permutations and stuff like that. And today I want to start that as a warm-up. I want to explain some result, which is, I think it's pretty cool. It's not going to be used in the midterms or in the homeworks or whatever. It's just a curious fact, which I wanted to mention since we're talking about generating functions. So yeah, the new subject is counting permutations. Yeah, so counting permutations. And well, so this is not in the, well, you can find it in what I'm going to explain in the Stanley book, but not in the, I think it's not in the Bona book. So we already know that there is an n factorial permutations, but let me try, I'm going to count various specific kinds of permutations. And the one I want to start with is slightly, the definition is very simple. So a what is it, a down-up permutation. Permutation W is down-up if it satisfies W of 1 is bigger than W of 2, less than W of 3, bigger than W of 4, etc. Similarly for up-down permutations. It is up-down, up-down, if all these inequalities are in the opposite direction. So that's it. That sounds like a kind of childish, kindergarten definition, but if you want to count them, you're gonna, it's gonna be tricky. But the first kind of easy fact, lemma, is that the number of, they are in bijection. So down, up, and up, down permutations are in bijection, which the bijection just sends W to W bar, which is defined by W bar of j is n plus 1 minus j for all j in bracket n. Which means that, so you kind of, what is this formula? You replace 1 by n, 2 by n minus 1, and etc. So you kind of, you just flip each number upside down in the interval bracket n, you reverse the order basically, and then all these inequalities are going to be reversed. So in particular, these sets are in bijection, so let E sub n, I'm going to define, these are called, I think, Euler numbers, but we're going to, I'm not going to call them Euler because then you're going to get confused, because we're going to have Eulerian numbers in the next lecture. But anyways, it's the number of down-up permutations of bracket n, or which is the same as up-down permutations. So let me give you an example. An example is, if I want to say, let's say n equals to 4. So I want to write down all down-up permutations, and I have all down-up and up-down on the left. 2, 1, 4, 3, 3, 1, 4, 2, 3, 2, 4, 1, 4, 1, 3, 2, 4, 2, 3, 1, right? You just have to, 2, 1 goes down, 1, 4 goes up, 4, 3 goes down, and etc. And up, down, you just flip each of these permutations upside down. So you replace 2 by 3, 3 by 2, 1 by 4, and 4 by 1. 3, 4, 1, 2, 2, 4, 1, 3, 2, 3, 1, 4, 1, 4, 2, 3, and 1, 3, 2, 4. So yeah, and you get, you can count it for each n, and you get some nice sequence of integers. So what I'm going to try to do in the remaining 6 minutes is try to find the exponential generated function for these numbers. So let's say maybe f of x is the sum, n greater than or equal to 0, e sub n times x to the n over n factorial. So you can pause the video and try to guess, once again, what would be the answer for the generated function of such permutations. And I can tell you the answer right now. And I'm not going to prove it completely, but I'm going to give you a sketch which can be made into a rigorous proof. So the claim is that f of x is I don't know if you have guessed or not, but f of x is secant of x plus the tangent of x. You can go to Wolfram Alpha and check that indeed the Taylor series gives you the sequence of numbers I gave you in this table. So yeah, the 5 here is the five down up or up down permutations. And so I just wanted to mention this because I think it's, when I first learned this, I was like super impressed. Yeah, anyways, as I said, I'm going to give you a proof sketch because it's going to be slightly more involved than we usually do. Oh, by the way, before I do the proof sketch, let me explain that. Let me mention that the secant of x is an even function, and the tangent of x is an odd function. So in particular, the secant is responsible for even terms, and tangent even terms. The tangent is responsible for odd terms in this sum here. So if you only take the even ends, you are going to get the secant only, and the odds are going to give you the tangent. So yeah. Now, how do I prove this? Well, the idea is to start with a bijective proof and then do some. So it's a combination of a few tools. So suppose you start with let's say W is a down-up or up-down permutation of bracket n plus 1. So maybe I should try to give you some 4, 1, 6, 2, 7, 5, 9, 3, 8, or something like this. So maybe that's W. So what I want to do is I want to find n plus 1 in here. So let here n is equal to 8. So 1, 3, 4, 5, 6, 7, 8, 9. Yeah, okay. So let k plus 1 be the position of n plus 1 in W. So in this case, 1, 2, 3, 4, 5, 6, 7. K plus 1 is 7. K plus 1 is 7. So k is equal to 6. And now let S be the set of numbers to the left of n plus 1. So this, in my example here, S is the set 4, 1, 6, 2, 7, 5. And bracket n minus S, which I'm going to denote by S bar, is the numbers to the right of the n plus 1. So the n plus 1 is special. The numbers to the right, as I said, it's 3, 8. Okay, so what I want to say is that W is split into 2 permutations, and well, I don't know whether it's the first one is down up or up down, but I know that the last one is going to be it's going to be up down, I think. Yeah. So so let U be the permutation of S, and V be the permutation of S bar. So U is to the left of n plus 1, and V is to the right of n plus 1. Yeah, so So the claim is that V is an up-down permutation of S bar, and also the reverse of U is an up-down permutation of S. So here by reverse, I mean if you just read U in reverse, it goes 5, 7, 2, 6, 1, 4. So it's if you just read these letters in the reverse order, it's going to start up, down, etc. So yeah, and any triple of S, U, and V can be obtained uniquely in this way. So you get n choose k choices for S, and then ek choices for U, and then en minus k choices for V. And then you can combine them together to get en plus 1 choices for W. So you get a recurrence, which is very similar to the Catalan numbers recurrence. Get recurrence twice en plus 1 is equal to the sum for k from 0 to n. Right? Okay, n choose k times e sub k, en minus k. So, okay, once for the Catalan numbers, we had a similar recurrence without the extra 2. Now you can convert this recurrence into an equation on exponential generated functions. So remember, if f of x is the sum en x to the n over n factorial, then, well, you can write, let me try to interpret the left-hand side first. And I claim that the left-hand side is 2 times f of f prime of x. It's twice the derivative of x, right? So what is twice the derivative of x? It's the sum over n greater than or equal to 0, en plus 1, right? So if when you take the derivative of x to the n over n factorial, you get x to the n minus 1 over n minus 1 factorial. So taking the derivatives of exponential generated functions just corresponds to shifting the indices by 1. X to the n over n factorial, and then there's an extra 2. Okay, there's an extra 2 coming from here. So that's exactly the left-hand side. For each n, the coefficient is exactly the left-hand side. And on the right-hand side, we just have the product formula. So that's the left-hand side. For the right-hand side, we just have the product formula f of x times f of x. And that's basically it. With the only exception, well, I have to take into account the initial conditions, I think, right? So I think there should be an extra one. Yeah, there should be an extra one just for some initial condition reasons, like when n is equal to 0. Yeah, when n is equal to 0, this is only true for n greater than or equal to 1. So I have to have an extra 1 for the right-hand side. So the equation on f of x is twice f prime of x is equal to f of x squared plus 1. This just comes out, literally out of the recurrence. Comes out of the recurrence. And yeah, so those of you who know calculus very well, or what is it, analysis, anyway, it's a differential equation. Differential equation. And because you can just take in the constant terms or whatever, you can get the initial condition. Initial condition is that f of 0 should be equal to 1. Just because f of 0, yeah. Yeah, so that's it. You have a differential equation, you have the initial condition, so it's unique. There is a unique solution, which is, you can check easily that the unique solution, I mean, calculus-wise, there's a unique solution, is given by secant of x plus the tangent of x. And the reason this is a proof sketch, because I have not justified, solving ordinary differential equations in terms of formal power series. But it's not hard to make this completely rigorous. Right? You can, when you solve a differential equation like this, it gives you some sequence of equations on the coefficients, and it's easy to check that it can be solved exactly. So yeah, that's it. That's all I want to say. I'm a little over time, which is, I guess, all right for a pre-recorded lecture. So I'll see you all on Wednesday, and thanks for joining the lecture.